This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Okay, so good morning everyone. It's Ash Wednesday today, and as you can see it's rather bleak, so let's talk about light, right? So yesterday you've seen the historical talk about lensing in particular, and today I want to discuss the theory behind lensing. So the first lecture I'm going to talk about lensing from the point of view of general relativity. And now of course we've been discussing the deflection of light. Now of course when I talk about deflection of light, I really mean deflection in space, right? So we have to find a way of going from the space-time, 4 dimensions, down to some 3-dimensional actual space in which we can talk about the deflection. And that's the subject of optical geometry. Okay? So what I'm going to do today in the first lecture is to discuss Fermat's principle. Of course, what form it takes in general relativity. And then we move on to optical geometry. But in order to actually do some real calculations, of course, we have to specialize the space-time from which we start. And that will just be the optical geometry corresponding to static spacetimes. And these optical geometries are actually Riemannian. And then within this framework of Riemannian optical geometries, I can actually discuss lensing, and we'll see that lensing is a global effect. So you'll see how topology of the particular surface that we will look at actually determines whether we can have multiple images and what the deflection angle is and so on. And the technique to use to discuss global properties there is the Gauss-Bonnet theorem. So that's the final topic. Of that first lecture. Now, I think it's probably useful to remind ourselves of Fermat's principle in classical optics. So what does Fermat's principle say? Well, actually, there's an earlier form which goes back to antiquity by Heron, which says that light always takes the shortest path. So the shortest path in space, well, that's only true if you have a homogeneous optical medium. But more generally, Fermat observed that light always takes the shortest path in time. Right? So the statement is if you integrate along possible paths, and of course the time it takes to traverse a length of path, which is be the speed times dl, right? And the speed is given by, actually 1 over speed. It's the speed of light divided by the refractive index n. This will be 1 in vacuum, or will be a number greater than 1, and that can depend on space. So now, if we look at the variation of this, and look for stationary curves, then these will correspond to actual light rays. Now, of course, this formulation of Fermat's principle does not work in general relativity, because the length, the full length in space-time for null geodesic is 0, of course. So we have to find a way of rewriting this in general relativity. Okay, now in order to do this, let's just look at stationary spacetimes. I'm not sure if you've covered stationary spacetimes in the lectures in detail. So our setup, so we look at spacetime. So that's a 4-dimensional differentiable manifold endowed with a Lorentzian metric. And the signature I'm going to use will be minus plus plus plus. Like this, right? And I'm going to work in local charts, of course. So I'm using the Greek indices to denote coordinates in the space-time, and Latin indices like this to denote spatial coordinates like this, right? And mu then runs from 0 up to 3. Okay, so sort of basic setup. Now, what's a stationary spacetime? So definition. So it's called stationary spacetime if it has a time-like killing vector field. So let's call this T. And so I think you've come across the notion of killing vector fields in the lectures, or certainly in the tutorials. So what this means, of course, is that, first of all, T is time-like. So with our signature, we want this to be the case. And for the vector field to be killing means that it corresponds to a symmetry of the metric. So the Lie derivative of the metric in the direction of T is equal to 0. Right? So you've seen Lie derivatives before, of course. So let's work out what this condition means. Right, so what are the components? Well, first of all, we get a term like this. And then we also have to look at the derivative of T's. And of course you get two terms. Like that. Right. Now let's suppose for our killing vector field we choose coordinates in such a way. So I use this notation for the basis that's coordinate induced. I guess you've seen that before. Right? So it's just a vector field that has components 1, 0, 0, 0. So as you can see then, these terms will go. And from this, we're just left with the derivative of the metric components with respect to time. Now all of that, of course, is supposed to be 0 for T to be killing. So you don't really have to use Killing's equation in this particular case. Of course, you can also do that. But we see now that the metric components do not depend on time. So I should rather say we can find a coordinate system in which the metric components do not depend on time. That's the stationary vector field. So we can now write down the most general stationary spacetime. So let me write it as a line element. Oops. All right, so what will this look like? Well, the point is we will have mixed terms in space and time. Right? Time, of course, and then a Riemannian metric in space. You can write it like this. Right? So you can see all the possible metric coefficients are covered. Where this is Riemannian. Right? So it's a metric in three-dimensional space. It's just of signature plus, 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 of course. And this is the mixing term, mixing time and space. Right. Now the point is, of course, that these functions, v, the omega a's, and also the HAB do not depend on t. So the metric if we write it in component form, with the minus v squared, you get the minus v squared omega a's here, right? Of course, the symmetry, and then the HAB over here. Okay, thank you. Okay. So we need stationary spacetimes. We also need the notion of static spacetimes. I'm not sure you've seen this before, so now we have our time-like killing vector field, and the spacetime will be static if this time-like killing vector field is hypersurface orthogonal, as it's called. Now to define this or to write down the condition, you need Frobenius' theorem. It's a little bit fiddly. I don't actually need this for what we're going to do later. But for our purposes, that really means that in a particular coordinate system, there are no mixing terms. Right? So this really means just for us that the components G naught A are 0. Right? So i.e. this these components omega A also vanish. These omega A's actually have a nice geometrical interpretation. So they're the spatial part of what's called a twisting vector for the spacetime. Okay, so this is a stationary spacetime and a static spacetime. And now, of course, we want to talk about light. So let me first of all remind you about null curves. Right, so what are null curves? Let's call them gamma. So in principle, of course, they're maps from some interval of the real line, let's say, into your manifold. And then, of course, we want to use some parameterization. So we go back down to R4. And let's call the parameter L for length, if you like. So we assign to L x mu of L, right? And then the null condition is just to say that the tangent vector of the null curve has length 0 in our spacetime metric. And of course, as you know, we can write this as dx mu by dl d mu. And for short, I might sometimes just write x mu dot d mu, like this. Right? That's the tangent vector to our curve and the null condition. Now, out of all the possible null curves that we have, certain curves might be geodesics. Now, of course, you've seen the condition for geodesics. Right, we've seen this before. Null geodesics will be null curves which, in addition, satisfies obviously the geodesic equation. So we might write this as the covariant derivative of the tangent vectors with respect to themselves, so autoparallels, is equal to 0. Right? That's our condition for null geodesics. So now I would like to move on to Fermat's principle in general relativity. We've got all the basics set up now. So let's consider a null curve again, right, with the null condition. And suppose we integrate it along the null curve. Well, of course, that's still going to be 0, right? And I would also like to fix the interval. So our real interval, let's just say our parameter L only goes from 1 up to L, from 0 up to 1, I mean, right, like this. So this will always be true for null curves. Now let's see what happens when we take the variation of this equation. Well, if we take the variation, you've probably seen this, you can call this L, we get the functional derivative. Right, so we get the integral of the Euler-Lagrange equations times the variation plus, well, of course, then there's the variation at the start point and end point of our curve. So this will be dl by dx dot mu delta x mu, and then evaluated from 0 to 1 is equal to 0. Right? So you've probably seen this in the context of deriving the geodesic equation. Now, actually writing this down is slightly tedious. I'm not going to do it here on the blackboard explicitly. If you have problems doing this, we can do it later if you want. But what you will get is the following. So let's look at this term first. L, of course, is given by g mu nu dx mu by dl dx nu by dl. Right, so this is in our notation g mu nu x dot mu x dot nu. Now, the derivative with respect to x dot mu gives you two terms because of the symmetry. So this term then will just give us 2 times, well, g mu nu x dot mu. So we can write this then as g of well, we can write it like this. I'm not sure if I want to write it like this. Yeah, okay, doesn't matter. Let's write it like this. And then the left-hand side, you recover the geodesic equation. So we actually also get a factor of 2 overall, which you have to take out. There will be a minus sign. And we get g delta x times the geodesic equation. Right? So this is 2 vectors which are contracted by g in this way. That's the result. So now let's make some observations. Let's suppose, so here's our curve, and we look at variations, right, along the curve, and there will be variations at 0 and variations at 1, the end point of our interval. Let's suppose all curves start with no variation at the beginning of our interval. Okay? And then observe the following. Let's suppose all curves also have no variation at the end point. So really keep the curves fixed at the parameter value L equal to 0 and L equal to 1. And if this is true for all possible variations delta x of L, you see from this equation that this implies, right, this term vanishes, and we just get the statement that the integral from 0 to 1 of g delta x times the geodesic equation integrated along L is equal to 0. So if this is true for all variations, this really means then that nabla gamma dot is equal to 0. So we recover the geodesic equation, right? I mean, this is of course something you know. If you fix the variation at the start point and the end point for all possible variations, then this of course means that we're looking at a geodesic. But let's suppose we do not do this. Right? Let's suppose we're in a static space-time. So then we can find a coordinate system where time and space splits, right? We're still assuming that the variation at the start point is equal to 0. Let's suppose the variation at the end point is just in the time direction, right? So let's say delta x at 1 will just be some delta t times d mu. Let's look at this equation again, star. Well, from the second term, yes?
Could you maybe repeat the argument that we get geodesic there? Because I do not understand, because the metric is not positive definite. From the integral to the step below to the...
From the integral?
No, down on point A.
Yes, here.
Yes, because I thought the g is not positive definite.
Oh, no, but it's for all possible variations. Yeah, no, that's fine, I think. Non-degenerate, yes, that's the point. Yes. Right. So I mean, this is just the geodesic that you get from keeping the endpoint and the start point fixed for all the possible variations. But now I want to look at a slightly different case. I want to look at the case that, first of all, the metric is static, and the variation at the endpoint is just in the time direction. So delta x1 is delta t d mu. So 0, yes. Yeah. Right, sorry, I mean, so the picture is really just, we have our curve. All the variations start at the same point, but at the parameter value 1, the variation is just in the time direction. Yeah, like this. Of the Killing vector field, yes. There we go. Exactly. So let's look at star again. What does star imply? So let me write it down. So I cancel the 2's, of course it doesn't really matter, or let's write it like this. Okay, so writing this in components gives you g mu nu del x mu gamma dot mu. Evaluate it for 0 and 1. Right, so this will be g mu nu del x mu at 1 times the tangent vector to the null curve at 1 minus, well, the same evaluated our starting point, that's 0, right, by our assumption, the variation at the starting point is 0. Now, at 1, the variation, we say, is only in the direction of the time. So this then will be 0 nu delta t gamma dot nu at 1, right? But remember, our space-time now is supposed to be static. And in the particular coordinate system that we have, there are no mixed terms, right? By staticity, right? The 0a terms are, yes?
Is there in the star one, shouldn't there be an evaluation at the right term? Because now we're evaluating it from 0 to 1.
Yeah, that's right. Yes. Yeah. Thanks. Right, so by staticity, g naught a is equal to 0. So out of this sum, only one term actually survives, and that's the g naught naught term. So g naught naught delta t gamma dot 0 at 1. Right. But now we have a static space-time. We can certainly assume that the g naught naught term is non-zero. We can certainly assume that the time component of the tangent vector is non-zero, right? So we're now allowed to rearrange this equation here. Right? We're allowed now to divide by those two terms. That's the crucial observation. It will be true in static spacetimes, not necessarily in other spacetimes. We can now write dt is equal to 1 over g naught naught gamma dot naught at 1 times, well, times this integral over here. Right? So this is what we've derived from star. That's the outcome of our variation. But let's think about what this actually means. So if we have an arbitrary null curve, we start with no variation at the start point. We get this equation for the variation in the time direction, the killing direction, at the end point for static spacetime. Now let's suppose our variation was not actually about any arbitrary null curve, but actually a null geodesic. Well, of course, we have seen from A, or I mean, as you know anyway, that this equation is true. So now for B, so suppose the variation was about an actual null geodesic, then of course from star we see that the right hand side just vanishes, right? So because of the geodesic equation, we see that delta t, and remember this was at the end point, is equal to 0. So an innocuous result, but that's actually Fermat's principle for static spacetime, right? So it rather looks like Fermat's principle that we've seen before. I've also written down the variation of t equal to 0 essentially earlier, but now it's different. So what exactly is different? Does anyone want to comment? So how does this really differ from Fermat's principle in ordinary optics?
The speed of light is constant.
Right. That's true, of course. But so remember what I said earlier. In ordinary optics, what is stationary is the total travel time of the light ray. Now, of course, the length of a null geodesic is 0. It's not the total travel time that's stationary in GR. It's actually the arrival time that's stationary. That's a local property. So you can see that it makes sense in general relativity. We're not looking at the whole of the null curve. We're just looking at the arrival time. That's stationary. Okay, so let me make the statement over there. So that's a theorem. So it's essentially Fermat. Now, of course, Fermat has not used that language, but that's what it boils down to in GR. And it's actually true for stationary spacetime as well. So for stationary spacetime, null geodesics satisfy that the variation of the arrival time is equal to 0, so the stationary arrival time. And the proof of this, well, I mean, for stationary spacetime, that's actually quite complicated, but for static spacetimes, you've basically seen it. We've gone over the argument, right? So we've done this. Okay, so this is Fermat's principle. Yep. Oh, yes. Yes.
Can you explain the physics of this equation? The variation of the arrival time is 0. This means does this imply something about eigentime, or is it just that two photons which were radiated at the same time somewhere back in the universe arrive at my photoplate at the same time?
Not necessarily. So it depends on whether they were emitted at the same time, right? I think I can show you an example later. Let's go back. So now let's look at what this means for our problem of defining spatial light rays in general relativity. Right, so let's go to the problem of optical geometry. So by Fermat's principle, we know that light rays correspond to curves which satisfy this condition, I mean, in the way that I've explained it. Now, what is actually this T for stationary spacetimes? So earlier in the lecture, you've seen the most general form for stationary spacetime. Let's just solve for dt. And, well, I mean, that was, I guess, was rubbed off now, due to my huge handwriting, I'm sorry. Anyway, so the term would have been, what would have been, plus or minus it would be something like this, right? Yes? That's the variation. Sorry, it's the same as here, right? But as we've seen, variation of the arrival time. But now, of course, in order to compute this, we would look at the, the time interval of our line element. So for stationary spacetime, this would be the time interval of the line element. In order to determine the light rays, then we would integrate this, right? We keep the emission time fixed, and then vary, right? So actually, light rays are, of course, that's just the geodesic procedure. Light rays are geodesics of this line element, right? Now, this looks rather unfamiliar. We have a Riemannian bit here, right? But here we have something else. It's a one form, really, isn't it? So dt is not really given by a Riemannian line element for stationary spacetimes in general. There's an additional bit. So you can see now that the geometry of spatial light rays for stationary spacetimes is actually rather interesting. It's not Riemannian geometry at all. It's something more general. And actually, this is a line element for something called Finsler geometry, which you may have heard before. But I'm not going to go into details of this. So if you later in the course maybe do rotating black holes, Kerr black holes, this is what describes the light rays in Kerr. But now, in order to do calculations here for this lecture, we'll just go back to static spacetimes. For the spacetimes that we have proved Fermat's principle. So again, we take omega A to be equal to 0. And then, of course, the metric you can see becomes very easy. The optical metric is just a Riemannian metric, right? Riemannian metric of three-dimensional metrics. Yes?
I got a little bit lost. I don't see where from you get this formula for dt.
Oh, I'm just solving for null geodesics of the line element we had before. So remember, we're stationary space-time, ds squared is equal to minus v squared, and so blah, blah, blah. Right, so I've written it down earlier. Sorry, it's been rubbed off, of course. We're just looking at null geodesics, so ds is 0, right? Null condition. And then rearrange, solve for dt, right? So the spatial light rays are actually geodesics of this optical metric. So let me just summarize. So we have null geodesics in space-time. Right, so let's suppose we have a static space-time. This is where omega A is equal to 0. Or we can have a stationary space-time. This is where omega A is non-zero, let's say. This corresponds to an optical geometry, so the geometry of the spatial light rays. By Fermat's principle. And then for static spacetime, as you can see, this is Riemannian optical geometry. And for stationary space-time, it's more complicated. I'm not going to go into the details of this, of course. This is a Finsler's metric of particular type called Randers. So Randers, Finsler, Randers. Was actually introduced early on, back in the 1940s. Randers used a line element like this to describe space-time. So he wants to introduce a preferred direction of time in a space-time context. Now, of course, that's not, Lorentz symmetry, of course. But anyway, here it certainly arises in the context of optics. But from now on, of course, we'll just look at static spacetimes in order to actually do calculations. So for static spacetimes, we can see from what I've written down over here, the line element will be dt squared is h ab over v squared dxa dxb, right? Now we have a line element in three-dimensional Riemannian space, where this is called the optical metric. Let's call it, I don't know, g twiddle, ab dxa dxb. Is optical metric. So it's a Riemannian metric, just with the signature plus, plus, plus. Yes?
I have a conceptual question.
Mm-hmm.
I mean, the difference between static and stationary.
Uh-huh.
It was here defined, but nevertheless, can one choose where to look at, or is it given by the direction in which I send the light ray? If it goes into a black hole, can I still say I'm choosing a static or a stationary frame where I'm looking for, or is it a property of the light itself?
In this particular case, it's really a property of the space-time itself. So the space-time as a whole is a static space-time. There's also the notion of a let's say, a stationary observer. So you can, if you look at the motion, let's say, in the space-time of a black hole, you can define observers that are fixed with respect to the coordinates, rather than freely falling. So there are various ways of defining static stationary observers. But that's the property of the entire space-time. It's a special space-time.
So then the case of stationary space-time is not important for us, because space-time has that property.
No, only certain.
To look for that case, and when do we have to look for the other?
So it's only true for certain space-times, which are static or stationary. So I will now move on to the Schwarzschild space-time that you've met before. That's a particular example of a static space-time. Right? And there are also stationary space-times. For example, if you have a rotating black hole, a Kerr black hole, that would be a stationary space-time. But it's a property of the entire space-time. Okay. Right? So now to actually do calculations, let's look at Schwarzschild. Yes?
One could say that if you have a rotating black hole,
Mm-hmm.
it's not a static space-time, it's only stationary. And if there you aspire to understand what the light does in space-time, if you aspire to understanding this pushed down into a spatial picture, then you're faced with considering a spatial picture with this Finsler geometry. You cannot understand it with the Riemannian geometry in space.
Mm-hmm.
Talking about light. That's the idea of this.
And that's basically because in the stationary space-time you have a preferred direction. Right? Because of the rotation, let's say, of the black hole, there's particular directions that actually matters for the null geodesics whether they go one way or the other way. So you get two different directions, and that's encoded by this omega A. In the case of a stationary space-time like Kerr, this then would actually depend on the angular momentum of the black hole. But anyway, this is all far too complicated. Let's just keep it simple and look at the Riemannian optical geometry of Schwarzschild, right? So for Schwarzschild, let me write down the line element, which you've seen before, of course. Oh, oops. All right, so that's Schwarzschild in all its glory. the line element in space-time. Now, what's the corresponding optical metric? So optical geometry. Well, we do the same thing as before. We're looking for null geodesics in space-time. ds squared is equal to 0, right? We rearrange for t, if you like. So, excuse me, you can immediately see dt squared, is what? Is dr squared over 1 minus 2m over r squared plus r squared divided by 1 minus 2m over r into, well, the round metric on S2, right, in Schwarzschild coordinates. And, well, as you know by symmetry, every plane through the center of the coordinate system is a totally geodesic submanifold. So the light rays will actually stay in a plane, in any plane through the origin. So without loss of generality, we can exploit the symmetry. We can set theta to be equal to pi by 2. In other words, we're on the equatorial plane, if you like, but really any plane through the origin will do. And then the problem becomes even simpler, right? We're just left with dt squared is equal to dr squared over 1 minus 2m over r all squared plus r squared d phi squared divided by 1 minus 2m over r. And then again, from what we've seen before, by Fermat's principle, we know that spatial light rays will be geodesics of this optical metric G twiddle AB. Right. Written in a simple diagonal form. So it's just got, I'll write it down. Right, it's really just this diagonal metric. So it's the metric of a surface, right? Very simple problem, but how can we understand geodesics of the surface? So of course one way of thinking about a surface when you're given a line element is to try and embed it isometrically in high dimensional space, right? That's a surface, two-dimensional. Let's try and see what it looks like by embedding it isometrically in R3 or E3, right? Oops. So in three-dimensional Euclidean space, what does that mean? Well, you probably know this anyway. So here's again our line element. So what we want this to be is, it's an isometric embedding, we want this to be the Euclidean metric in three-dimensional space. Let's say, I mean, by exploiting this symmetry that we have, let's say we look at cylindrical coordinates, right? So we want something like dz squared plus dr squared plus r squared d phi squared. And well, it probably makes sense to identify the polar coordinates. We use the same polar coordinates in the optical metric as well as in our embedding geometry. So we identify the phi's. So that of course tells us that the function big R, which will be a function of our little r's, will be given by, well, let's say R over square root of 1 minus 2m over R, right? And of course what we would like to determine is a function of z, z is a function of big R, right? And then we have a cylindrical polar equation E3, and then we see what the surface actually looks like. So now, well, by rearranging then you see that we have to determine 1 over 1 minus 2m over R all squared is equal to, those terms go, we divide, is equal to dz of R by dr squared plus dr, big R of little r, by d little r all squared. Okay, so in principle you can see how to do this. We have big R of little r, we can work this out. So we can determine dz by d little r. I mean, it's just algebra, you can rearrange it. I'm not going to do it now. But of course what we like to do is we like to express this as dz by d big R. And what you will find is the following. It's 4mr little r minus 9m squared divided by little r minus 3m all squared. Right? And all of this is in terms of little r. You should actually also express in terms of big R. But you can see that's not easy at all. Right? You really have to integrate, invert, and so on. But we don't actually need to do this. We can look at this expression and find out about what this embedded surface actually looks like. So let's note a few things. Well, first of all, this embedding will only work if the numerator is non-negative. Right? So the embedding works if little r in our original optical coordinates is greater than 9/4 of m. And as you will observe, of course, this is actually bigger than 2m, 2 1/4, right? So even though the optical geometry is defined all the way to the horizon, to the event horizon, the embedding, at least in these coordinates, only works up to 2 1/4 of m. So it stops a little bit before the horizon. But I mean, physically, that is not actually important. What else can we see? What about the asymptotics? So let's suppose we go to great distance, long way away from the Schwarzschild black hole. You see from this equation immediately that big R is essentially little r. They approach each other. And then we also see that dz by the little r will go to what? Will go to 4m divided by r. So then in the limit we can also write it as 4m divided by big R. That's of course square. Right? So you can see what z of r will look like in the limit. We take the square root. So this looks like 4 square root of mr. Right? I think that's right.
Isn't the embedding only for r bigger than 3m because there is a singular?
Yeah, I'm coming to this. Yes. No. Yeah, okay. Yeah, I'll come to it. So anyway, at large distance, you see the surface will actually look like, like the square root of r. Yes, what about this point? We see dz by dr diverges at little r is equal to 3m. Now actually this is not a problem if you write in terms of big R. You just have to believe me. You can do it if you change the coordinates. What this means, however, is that there's a photon orbit. You might have seen this in your tutorials in Schwarzschild. So it's the radius of a circular photon orbit in Schwarzschild. So we've now got enough information to sort of draw it. At large distance, it looks like, like a square root function. So this is now z, right, as a function. So in the plane of big R and phi. Then there is this throat. Right, this is at little r is equal to 3m. And the embedding breaks down a little bit further in. Let's say here. This is little r is equal to 9/4 of m. And that's what it looks like. Okay. So it's got this interesting shape with a throat, a waist here. And now the statement again from Fermat's principle is that spatial light rays will correspond to geodesics of this surface. Right? So it's really what it says. Let's suppose we have a light source which will be sitting somewhere here. We have an observer sitting somewhere else. We work out the geodesic on this surface. Well, that's going to be a light ray. Okay.
So this little 2 by 2 metric you derived before is the pullback of the three-dimensional Euclidean metric to this surface.
I think it's right, yes.
So you constructed this surface in order for us to have an idea of
That's
what
right.
this metric
Yeah,
is.
yeah, yeah, of course. Right, so we want to see what this looks like, get some intuition. It's an isometric embedding, right? So therefore we can talk about geodesics of this particular embedded surface in the same way. Yes. Okay. Sorry, question?
Yeah.
Yes.
I mean, the interpretation of this set, is this now something like a distance from the black hole, or what? How can one interpret this?
Yes, quite an optical distance.
Optical distance.
And of course, at large distance, it really just becomes spatial distance, because obviously in Schwarzschild, as you move far away, you're basically in flat space, right?
Yeah.
So really the optical distance, and in vacuum, the optical distance is really just the Euclidean distance in this picture. But as you move closer to the horizon, this is what it looks like. And of course, we want to determine, yes?
Can we really assume a static or stationary spacetime in the proximity of a black hole? Isn't that a bit dangerous?
Well, no. So the spacetime the spacetime is static. We're outside of the horizon, right? Is this what you mean? So there's a limit of staticity, but all what we do is certainly outside of 2m, and the spacetime is perfectly static. In the Schwarzschild case, it will be stationary. In the case of Kerr, right, outside the Ergo region, certainly. Okay.
I have one question.
Yes?
The last multiplication error on the left-hand side.
This one.
I didn't see.
It's a bit tedious. I'm not going to go over it, but in principle, you can see how to do it. R of R, we have read off from this identification, right? So you can differentiate. You get one complicated expression in terms of little r. Then you can solve for dz by dr in terms of little r, right? This is something you can write down. But then you can use the chain rule. Oops. Well, actually, I can write down over here. Like this, right? And we can just write down dz by d big R in terms of dz by d little r with this factor. But of course, we can simply get it from here, right? It's not a problem. The problem is actually to write this expression on the right-hand side in terms of big R. That's even more tedious. But there's no problem in getting to this. Okay, so now we want to discuss, lensing in some sense, the deflection of light rays. Now, in order to do this, we have to understand how the curvature of this surface impinges on the propagation of light rays, right? So let's think about that. Curvature in light rays. And the quantity that is actually interesting for us is the Gaussian curvature of this surface. So you may or may not have seen the concept of Gaussian curvature before. Geometrically, it's the product of the two principal curvatures. Now, if you look at the surface and you sort of know the background, it's immediately obvious that the Gaussian curvature of the surface is everywhere. Does anyone spot it? Negative. Right? So we have two principal curvatures. We have if you like, we have a curvature in there it goes. We have a curvature in this direction, so curving in, and we have a curvature in that direction going out. That tells you the two principal curvatures have opposite sign. The Gaussian curvature is the product, so the Gaussian curvature is actually negative everywhere. And this is very surprising if you think about this, but I'll come back to this later. Anyway, let's look at what Gaussian curvature actually is and why it's negative on the surface everywhere. So you've seen curvature, of course, in terms of the Riemann tensor. The notation might be slightly different. I'm used to that. But you'll see that everybody does it differently in books, so you just have to get used to it, right? So that's what I do. And this is for vector fields that commute. And writing it in terms of a coordinate-induced basis, this is how I read off the components, so it's A, B, C, D, del A. So very, very straightforward. And now what's Gaussian curvature? Now, of course, this is a property of a surface, of a two-dimensional manifold, right? Gaussian curvature of a surface. Now, you're familiar with the symmetries of the Riemann tensor. How many independent components does the Riemann tensor have in 2 dimensions? One, right? So if you write down R, A, B, C, D, you know you have antisymmetry in the pairs and symmetry of the pairs. And of course, if you only have 2 coordinates, there's just one combination that's going to be non-vanishing, right? And this number we call the Gaussian curvature. Of course, you have to, it's defined up to a sign, so I define it like this. It's K, Gaussian curvature K, into, now we have to respect the symmetries. Of course, that's G, A, I think it's AD, GBC minus G, AC, GBD, like this. And that's the Gaussian curvature. So let's suppose, to be a bit more general, let's suppose our surface is parameterized by U and V, coordinates U and V, and we have a line element on the surface that's given by du squared plus f of u squared dv squared. Right, so it's a symmetric surface. So it's a useful formula that you can use in more general context. Of course, we want to apply to that particular optical problem. But let's say we have a surface given by this line element.
Sorry,
Yes?
why are you allowed to set the commutator to 0?
I'm just looking at commuting vector fields. So everything commutes. All the vector fields, these vector fields commute. So you know if you have a coordinate-induced vector field, of course that vanishes. So then, if you like, it's a lemma. So the Gaussian curvature of this surface has a very simple form. It's simply given by minus the second derivative of f divided by f. So it's a nice little formula. So let's try and prove this in general. Let me see. Okay, proof. So we have to work out this Riemann curvature tensor for this very simple metric. It's like an exercise, right? Well, first of all, what are the non-vanishing connection components, the Levi-Civita connection components for this metric? What's the metric? So this is G twiddle. Well, it's simply 1 f squared of u, 0, 0. Right? It's a diagonal metric, very simple. And you can convince yourselves that there's only 2 non-vanishing connection components. It's v u u and v u v, and everything is 0. So what are they? Well, this will be a half gv. Well, it's a diagonal metric, so we're only left with gvv upstairs, and then g v u comma u, 2 of them, minus g u u comma v. Well, of course, there are no off-diagonal terms. That goes. So we're left with a half times 1, right? What's the inverse metric? It's just the inverse of a diagonal metric. It's just the metric of the diagonal components, 1 over the diagonal components. So it's a half times 1 times minus the derivative of this with respect to, oh, sorry. It's the other way around, actually. Huh? Is this right? Sorry, yeah. So it's UVV. Ah. Right. Yeah, that makes more sense. VV comma U. Right. So a half times GUU, that's 1, right, times minus GVV divided, differentiated with respect to u. So this is minus 2f primed. So this is, yes, that's right. It's minus f primed. Is this right? Everybody agrees?
Why this term disappeared?
Sorry?
Why this first term in brackets disappeared?
Well, because it's an off-diagonal term, right? With a diagonal metric. And the other non-vanishing connection component is actually this. So it's a half GVV upstairs now into what? GVU, V plus GVV, U minus GUV, V. These are diagonal terms, they're 0. Now we're left with a half times, well, GVV upstairs is 1 over f squared, and this is GVV, U, so this is now again f primed. So now we get plus f primed over f. Okay? Yes?
I guess it's just a comment that so there's no summation notation, obviously, because...
Right, no. Yeah, that's just notation. I mean, I guess you've seen, notations like this. In terms of the coordinates, here we just have 2 coordinates for the surface. Yes, of course there's no formation. Right? Like I said, these are the only 2 non-vanishing connection components. So now we can work out the Riemann tensor. Well, what about RUV UV? Well, this will be K into GUV GVU minus GUU GVV, right? What is that? Well, that's actually K times minus the determinant of the metric, G twiddle. So we see now that the Gaussian curvature K is actually minus the component R UV UV divided by det G. Well, I'm afraid we have to work it out. What is det G? It's just f squared, right? So it's minus 1 over f squared into, well, this component of the Riemann tensor. Now we have to write it out. Now again, that depends on the conventions you choose. I've chosen this convention. If you do this, you get gamma. Okay, actually, I have given you this component. Right, so I have to pull down one of the indices. Easily done, it's a diagonal metric. GUU is 1 anyway, right? So this is U, V, U, V minus gamma U, V, V, U plus gamma, U, V, U, A, V minus gamma, V, V, U, A, U. Right? In all its glory. There are no connection components that have a U upstairs and a U downstairs. We know immediately this is 0. This will be 0 too. So we're left with minus 1 over f squared into, well, gamma UUV is f primed over f. So that's minus f primed over f primed plus, okay, what about this? We have a U upstairs, V downstairs. The only connection component that survives will be the VV component, right? So out of this is now an actual sum, right, over A. But the only component that survives from the summation will be that. And this is equal to, well, minus f primed into f primed over f. So let's see, what is this? Something strange. UVV. Oh yeah, sorry. This is actually, this was minus FF primed. Yes, that makes more sense. So we get, from this we get a plus F double primed plus F prime squared minus F prime squared. They cancel, right? And we just get plus F double primed. So indeed, we do get minus F double primed divided by F as required. Right, so that's the proof. Nice little lemma. Yes, let's see that it actually makes sense. So example. Let's look at the sphere, the round sphere. Well, spheres are always round, right? I mean the sphere with the round metric. So let's say our surface is just given by that. Right, you know this. What's the Gaussian curvature of the sphere? Well, actually, you can think of the Gaussian curvature as 1 over the radius of curvature squared of a sphere that osculates your surface, an osculating sphere. Now, of course, if you have a sphere in the first place, the osculating sphere is the sphere itself. If it's a unit sphere like S2, of course, the radius of curvature will be 1, right? So we expect k to be equal to 1, and well, indeed it is. So, yes. Well, if you know Latin, of course, that's obvious. Osculum means the kiss, right? Actually, baculum. And, right? So it's the kissing circle, because it touches the surface, not just in the first derivative, but actually in the second derivative as well, which is all important, as you know, for these things. Anyway, sorry. So u is theta, v is phi. F of u, our strange function f, is just sine theta, right? So the Gaussian curvature, according to the lemma, is minus f double prime divided by f. So it's minus sine cos minus sine, right? So it's minus sine theta divided by sine theta. So indeed it is plus 1 as expected. Okay, so it makes sense, right? So now this is the Gaussian curvature, and I mean, I'll come to lensing after the break. Let's just, before the break, apply it to the optical geometry of Schwarzschild and see what we get. Right? So now apply to Schwarzschild, to the Schwarzschild optical geometry. Well, again, dt squared was, what was it? Was dr squared over 1 minus 2m over r squared plus r squared d phi squared over 1 minus 2m over r. Right. So now to apply this, we make another identification. We say, okay, let, well, certainly let v be equal to phi. And so we identify the polar coordinate again, excuse me. What about u? Well, we can certainly say that du, right, by comparing the respective first terms, du will be dr divided by 1 minus 2m over r. So we really have to express little u in terms of little r in order to work out the Gaussian curvature. And you can see that's rather tedious. You have to integrate up, change coordinates, differentiate, and so on. Let's try and be a bit more clever than this. So we know that k is minus 1 over f d squared f of u by d u squared, right? Now, of course, that's the same as 1 over f into d by du. Actually, it's right in terms of r, so I want to write as d by dr, dr by du, into dr by du, df of r by dr. Right, so changing coordinates. We can do it in the differentiation also, and you can see this is actually helpful, because if you work this out, what is it? It's 1 over f into dr by du, d by dr of dr by du, df of r by dr, right? Plus the other term, which will be this derivative acting on that, so it will be dr by du squared times d squared f of r by dr squared. And of course f of r we can actually read off from the line element, right? The way this line element was set up, this 4 factor here is f squared of r, right? Where f of r is really what? Is r divided by square root of 1 minus 2m over r. And everything is given. Now we can just plug it in. Right? Differentiating is always easier than integrating. We can certainly work out the second derivative of this. dr by du, we also know from our identification. What we mean by u, dr by du is what? Is just 1 minus 2m over r. And this again you can differentiate with respect to r, no problem there, right? Differentiating with respect to u would be more difficult. Anyway, you can plug this in immediately, just work it out, and then get the answer, and the answer is, after some work, k is equal to minus 2m over r cubed into 1 minus 3m over 2r, and that's it. So the terms collect nicely. And remember, we're in the static part of the space-time, of course, r, I mean outside of the horizon anyway, we're outside of 2m. This is 3/2 m. So you see the bracket is actually always positive, right? So we see the Gaussian curvature of the Schwarzschild optical geometry is indeed negative everywhere. So like I said before, if you know about principal curvatures of surfaces, it would have been immediately obvious anyway from the picture that I drew earlier. But now going through all these shenanigans, we can also see analytically that the Gaussian curvature is always negative. So before we stop for the break, let me just make one observation. So we know that the Gaussian curvature is negative. What does that tell us for the geodesics? So if you have a surface with a negative Gaussian curvature, remember the geodesics on the surface are our light rays, right? So if the Gaussian curvature is negative, this actually means that the geodesics have to diverge. They diverge everywhere. So how is it possible for the light rays to reconverge somewhere else so that you have multiple images, as you've seen in the pictures yesterday? And the answer is that's a global effect. So we have now got to connect the local properties of the surface, the curvature, to the global property of the surface, the topology, and we do this by Gauss-Bonnet. So I think I'll do this after the break. Okay, thanks.